Dear student, in today's lecture we are going to look the topic parser. As we have known that the parser is broadly categorized into two parts, top-down parser and the bottom-up parser. Let me see, the first one is the top-down parser. The top-down parser can be implemented by the two ways, with the full backtracking and second method is without backtracking. So in today's lecture we'll see that how the top-down parser without backtracking is implemented. So when we are going to implement the top-down parser means we are going to start with the starting node and we are coming downwards to the root leaf of that node. So this with the without backtracking method, in that the first method is called as the recursive descent parser and second one is called as the LL1 parser. This is also called as non-recursive predictive descent parser. Now, in this LL1 parser and the RDP parsers are implemented by using the without backtracking method. Means we are going to look out that which alternative we are going to use to solve that particular problem. So let me see that our recursive descent parser. In recursive descent parser, we are going to implement a one simplest method, that we are going to look out for the production rule. The production rule is consist of this LHS part and it is consist of your RHS part. The basic idea behind is that we are going to implement a one function, that the function name is nothing but that LHS and the function body is your that RHS, and we are going to look out that whether we are getting that particular terminal or not. Let me see that we are implementing this recursive descent parser for this example. So we are going to start with that E as in one function, means we are implementing the different kinds of function. Then E gives plus TE dash. So T is terminal, means we are going to call a function to this particular non-terminal. Second one is E dash, means we are going to call that E dash as in one function, E dash function. Now we are going to write down the function for your E dash. Then E dash we are getting plus. Plus is nothing but the terminal. For that purpose, we are going to write down a one function that is called as the match function, means we are going to give to that particular match. Later on, we are going to have that T and then E dash. Similarly, for our T, the T gives FT dash, so that's why T gives FT dash. Next one is T dash gives star FT dash, means T dash is a one function which consists of star is our token. That's why we are going to call a one match function, where we are going to compare the match. And then ft dash, that means calling to that function f, calling to the function ft dash. Like that fashion we people are going to implement. Then how does this match will work? The match function is nothing but that which will look out for the token. So match will take a one character. Let we are saying that the character is t. Then this t is going to be matched with, means if whatever the character t is going to be matched with our look ahead or not. If it is matched with this look ahead, then we are increasing that look ahead by 1. That means we are going to write down this statement that we are going to take that L as in one character is equal to get character, means we okay. And now that the main function is going to be start with our calling our starting symbol. So in this example we are having the starting symbol is E, so that's why we are saying that E starting symbol, and then we are going to check that if whatever the look ahead we are getting is equal to dollar or not. If it is matched with the dollar, then we are saying that the string is successfully parsed. If it is not, then we are saying string is not successfully parsed. We have seen that how we are going to write down the function. So for that given grammar, we are saying E gives TE dash, T gives FT dash, E dash gives plus TE dash, plus is the token, that's why we are matching with it, plus if it is matched, then we are calling that match function. The job of match function is which will increase the look ahead pointer. Then E dash gives TE dash, T and E dash are that non-terminal. Like that fashion we wrote this recursive descent parser for our algorithm given grammar. Now we are going to parse that given input string for this recursive descent parser. As our recursive descent parser will start with this main, so main is going to call our e function. That e is nothing but our starting symbol. And this is our input string. We know that the input string is end by the dollar. Now the look ahead pointer is pointing to our id, and main it starts with this e. Now e function is being called. E is called to our t. T is called to f. Now we are going to come back to this f. We are looking for if is the look ahead pointer is id? Yes, then we are calling that match id function. The job of match id function that if id is equal to, as L is the id and this t is id is equal to id, then we are going to increase the look ahead pointer by 1. Okay, so our look ahead is now plus. That means the value of L is plus. Now we are coming back from this match function to this f. F function is over. This f was being called by this t, then it is calling to that t dash. Now t dash is the L is the plus, so that's why it will not goes in this one. T dash will return nothing but then it will goes to t. Now after that t, the t is over. It was being called by this e function. That's why our next e dash will be executed. Now e dash is going to be called. E dash, the look ahead is L. L is the plus? Yes, L is the plus. Plus is equal to plus? Yes, then we are going to call that match function. Then the control reaches to this match. Then it will look out that look ahead is plus and t is the plus. If both are correct, yes, then our look ahead is being increased. Now look ahead is pointing to this d. Means we are looking for this particular d. This match function is over. The control is returned to this e dash. Now our look ahead L is nothing but id. Now e dash is going to call t. Now t is being called here. Now t is called to that function f. F is going to check out, is a look ahead is equal to opening braces? No, look ahead is id. That's why it will enter into this one. Match is id? Yes, that's why we are going to this particular match function. Id is equal to id? Yes, L is equal to get character. Means our id is not, our L is nothing but the dollar. Now this match function is over. Control returns to f. F is going to be returned to this t. T is going to call that again t dash. Again t dash, our L is the dollar. Dollar is not matched with the start symbol. That's why it will not enter into this t dash. Now the control is go back to this particular t. Now that this t was being called by this function e dash. Now the control is returned, come back to this e dash. Again it is going to call itself. The value of L is dollar. Dollar is not matched. That's why this will not be executed. This e dash was being called by our e. E is over. That e was being called by our main. Now our look ahead is dollar. This dollar. Dollar is equal to dollar? Yes. And we are saying that this id plus id, the string is successfully passed with the technique recursive descent parser for given EFT grammar. We have seen that how does RDP works. Let me move towards the next part, that is LL1 parser. LL1 parser is also called as non-recursive predictive parser. The major thing behind the top-down parser is that if we are going to implement any top-down parser for this given grammar. So look at this particular grammar. If we are saying that E gives E plus T or T, T gives T star F or F gives parenthesized D or ID. If we are going to pass the input string is ID plus ID for this given grammar, then what happens? We are going to always top-down parser starts with starting symbol. So we are going to use that E as a starting symbol. Then we have to use that production rule is E gives E plus T. As we know that this is that left factoring run. So we are saying that E gives E plus T. Again we are going to call that E, means again we are getting the output is E gives E plus T. So we can't implement the top-down parser for such a kind of that grammar. This grammar is called as left recursive grammar. That's why we have to eliminate this left recursion from this given grammar, and that grammar can be passed with help of your top-down parser. Let me see how that left recursion will be worked. The left recursive grammar is nothing but that, means if we are having the grammar is A gives A alpha or beta. Means we are going to start with our A. So we are getting the output is A gives A alpha. Again we are getting the output is A gives A alpha, and so on. Means on this left hand side it goes on increasing. Means this language can be recursively calling to this A continuously. That's why we have to eliminate the left recursion. The rule for eliminating the left recursion is very simple. We have to introduce a new A dash as an one factor. The left recursion is written that this can be written as A gives beta A dash. Those part which is not recursively being called, which has been written first, and introduce that new part A dash. Now what is A dash? A dash gives is nothing but, for this beta it can be either epsilon, but for this A alpha it will execute alpha A dash. So this is the rule to remove our left recursion. If we are having A gives A alpha or beta, then its elimination of left recursion is A gives beta A dash gives alpha A dash or epsilon. Let me apply this on this rule. So as we are having that E gives E plus T, then we have to compare with that A gives E plus T or beta. A gives A alpha or beta. A is our non-terminal E. That's why this A is equal to E, and alpha is nothing but that plus T. That's why this production rule is rewritten as E gives beta means nothing but that our T. B gives T E dash. And what is A dash? A dash gives alpha. Alpha is plus T. That means plus T E dash or epsilon. Right? Similarly, if we are looking for this T gives T star F. So this is what? Again left recursive grammar. So we have to eliminate it. So our rule says that if T gives T star F or F. If we are going to compare with A gives A alpha or beta, then T is nothing but that A, and alpha is nothing but star F, and beta is nothing but that F. So our rule is A gives beta A dash means nothing but that T gives F T dash. T is the starting symbol. And what is T dash? T dash is alpha A dash. Alpha is star F. That's why it is star F T dash or epsilon. F gives parenthesized E or ID. It is no any recursion. So our that modified grammar is consist of E gives plus E gives T dash, E dash gives plus T dash or epsilon, T gives Ft dash number 3, T dash gives star Ft dash or epsilon number 4, and F gives parenthesized E. So this is the modified grammar, or we can say that the grammar is free from that left recursion. Also, our top-down parser is also free from left factoring. So what is a left factoring? Suppose we have the grammar is A gives alpha beta 1 or alpha beta 2 or alpha beta 3 or alpha beta 4, and we want to parse the input string is alpha beta 4. So how do we start? We start with the starting symbol A, right? So we are saying this alpha beta 1. Now this alpha is matched. That's why our lookout pointer is increased to beta 4, but here we are getting beta 1. Means this alternative is not useful for us. Means again we people are performing backtracking. Then we are going for the next alternative. Next alternative is what? Alpha beta 2. Again this alpha beta 2 doesn't match. Then it is not applicable. Then we are going for this next alternative. This is called as the left factoring. How does this left factoring comes? Due to these common prefixes. At this moment, we are not able to identify that whether this first alternative is applicable or the second or the third and so on. So our top-down parser that should not contain such a left factoring problem. So let me remove this left factoring. In this left factoring, we have to identify that which one is the common part. So which is the common part here? Alpha is the common part, right? So that's why we are rewriting the grammar is A gives alpha as a common part. And then we will move towards that next A dash. What is the A dash? A dash is, if it is beta 1, then we are using beta 1, otherwise beta 2, otherwise beta 3 or beta 4 and so on. So this is nothing but we are saying that the left factoring elimination. Understand? So if we want to start with this alpha beta 4, then we are going to start with A gives alpha A dash. What is A dash? If we are using beta 1, so we are saying beta 1 is not applicable, means we are not using beta 1, beta 2, we are directly using beta 4. So we are getting this alpha beta 4, that input is successfully passed. Let me see another example for the left factoring. So this is the if else statement. S gives if expression T, that is then statement. Second alternative is if expression, then statement, else statement or A. And our E gives B. So here if you want to look out that this is consist of the left factoring. So which is the common prefix? IETS is the left factoring, or we can say the common prefix. So we have to remove it. So our grammar is becomes S gives IETS, that is alpha part, which is a common prefix, and then introduce new grammar, new symbol S dash. Now what is S dash? S dash gives either it contain the epsilon for it, or it contain ES, or it contain A. Sorry, we are writing this A is, as it is not the common factor. So this is what the left factoring removal. Okay, so I hope you understand that the basic important or the need for the developing this top-down parser is that a grammar should be free from left recursion and the left factoring. So what is a left recursion? That whatever the non-terminals we are getting on this LHS side, it is going to be immediate RHS, right? So this is called as the left factoring. Similarly, a grammar should be free from, this is left recursion. Similarly, a grammar should be free from left factoring. In next class, we will see how to implement LL1 parser